Yes, you're good. Great. So I can introduce you really quick. Jinsun is a PhD student at Georgia Tech researching edge computing with a broad interest in distributed systems and hardware architectures. They will present about their work towards a standardized representation for deep learning collective algorithms. So you can get started whenever you are ready.
Right. Thanks, Amanda. Hi, everyone. I'm Jinsun from Georgia Tech, and today I'll present our proposition on standardizing how to represent collective algorithms in distributed learning. Before I move on, I would like to acknowledge my collaborators from both Georgia Tech and NVIDIA, without whom this work would not have been possible. So basically today what I'm going to talk about is that there's been a lot of work in the distributed machine learning space, but they've largely been fragmented. And one key observation that we have is that collective algorithms have been represented using different schemas, different formats, and we're trying to call for a common representation for all of these different collective algorithms. So first I'll talk about a bit of a background on the distributed machine learning space and discuss the motivations on why we need a common representation, and finally move on to our approach on how we would make this possible, and finally discuss a proof of concept workflow that we've built with our common representation. All right, so as we all know, larger models have pushed for distributed machine learning. And this area introduced a co-design space that spans all the way from the workload to system, network, and compute. This figure represents a simplified version of the design space, which shows each part of the stack and corresponding topics to it. Some significant areas include optimization of the workload's parallelization strategy and the optimization of collective communication, which is to be issued across the network interconnect. Indeed, there have been several works that have tried to optimize these parts. For example, you see tacos and tackle, which are notable synthesizers which generate collective algorithms. And you have the MC-Klenk domain-specific language, which enables users to easily write their own custom collective algorithms. However, we observe an echoing concern that these works have largely been carried out separately and in isolation. So the collective algorithm works are focused only on the collective algorithms, and the workload works are focused on workload and so on. So here's our crux. Behind this separation, behind this isolation, we observe that a significant factor to this is that there is no common representation format across distributed machine learning workloads and collective algorithm tools. What this means is that the tools that suggest parallelization strategies use their own representation of the workload, and also the tools that generate or even consume collective algorithms all use their own different representation. And because the representation formats are different across workloads and collective algorithms, we lose the opportunity for the co-optimization of machine learning workload, compute, and communication. Also, the lack of interoperability, even within the domain of collective optimization, causes an increased engineering effort. For example, if you're a user using a collective synthesizer and you wish to simulate the performance of this new collective algorithm and verify it with real hardware using a runtime library, the synthesizer, simulator, and runtime library all use different formats to represent the collective algorithm, which means you as a user would have to go through significant engineering effort to make the connections possible. So what is our approach? Our approach is to create a common representation of collective algorithms based on the Chakra execution trace format. Now, Chakra execution trace, or Chakra ET, is a graph-based schema that is already used to capture workload operators and dependencies of real distributed machine learning. So on the top right, here is a sample toy example where a machine learning workload can be represented using operators such as compute, all reduce, all gather, and memory access operators, along with all of their dependencies. So let's take a step back and talk a little bit more about Chakra in detail. So Chakra is part of the ML Commons initiative, where several industry participants gather to forward efforts in the machine learning space. The key observation that many people feel is that there is a demand to study real industry workload, the patterns, how the workloads are executed, like what patterns exist in the workload. But it is difficult for industry to naively share these information because naturally the industry participants don't want to share proprietary data. And here's where Chakra steps in. Once industry participants run their normal AI workloads in their production environment, they can generate execution traces with timing information using support from libraries such as Python. Then, once going through the obfuscating stage that we provide, that Chakra provides, once proprietary data is hidden, we have what we call the Chakra execution trace, which holds the dependency and the operators without revealing hidden data, as I've shown before. This, along with a set of tools that the Chakra working group provides, allows the open source communities and also the research community to study the execution trace of a real workload using a wide variety of tools such as benchmarking or simulators. Vendors can then combine the insights gained from the open source or the research community with their own proprietary simulators and emulators, further using the insights generated from these studies. On the top right side are links to the Chakra paper and the working group for anyone who's interested in learning more about this. But now back to our discussion. To reiterate, our proposal is to extend this format, to extend the format that is already being used to represent machine learning workloads, to also represent collective algorithms across a wide variety of tools. As you can see on this pink box, we take existing primitives in the Chakra schema, such as send, receive, and compute, to represent collective algorithms as a sequence of these operators along with their dependencies. So here's an example of how the conversion from the collective algorithm to the Chakra execution trace works in a bit more detail. Let's look at a ring-based all-reduce across 4 nodes. On the right-hand side over here, we see the Chakra graph of a single node, which represents the first message with the send, receive, and computation primitives. Additional messages are also represented with more operators along with their dependencies. Note that in the all-gather phase for the all-reduce algorithm, we don't have the computation operator since we don't have a reduction phase. And also similarly, the Chakra execution trace can be used to represent a halving doubling algorithm as the all-reduce using a sequence of send, receive, and computation operations along with their dependency. Now, one thing to note is that the graph of halving doubling looks a little bit different from the graph of the ring algorithm, naturally because the halving doubling algorithm has a different sequence of operators, a different sequence of dependencies compared to the ring algorithm. So again, with that in mind, I would like to once more highlight that with the Chakra execution trace, we are able to represent an arbitrary collective algorithm. It doesn't need to be ring, it doesn't need to be halving doubling. It can be an arbitrary algorithm using the send, receive, and compute operators that we have at hand. What this allows us to do is to generate a large graph by replacing communication nodes such as the all-gather node or the all-reduce node with the Chakra representation of the collective algorithm. This large graph encompasses both the collective and the workload information. And by studying and modifying this graph, we can easily study the co-optimization of workload and communication. Also, the standard format can be used across different collective algorithm tools, removing the need for unnecessary engineering efforts. One of the tools that can use this common representation would be the AstraSim simulator. The AstraSim simulator is an actively maintained simulator built in our lab that can simulate aspects across a stack of the distributed machine learning space. The simulator traditionally takes as input the Chakra execution trace of the workload and issues simulated commands in accordance with the operators and their encoded dependencies. These operators are then further simulated using existing network, memory, and compute simulators, such as NS3 or ScaleSim. AstraSim provides a set of APIs, a set of network, memory, and compute APIs, which allows users to use different network, memory, or compute simulators in a plug-and-play manner, therefore being able to simulate aspects across this whole stack with a wide range of fidelity and simulator speed. We also have a tutorial on the AstraSim simulator tomorrow at 3 p.m. Pacific time. So if anyone is interested, please feel free to join the tutorial or refer to the website on the top right side. But back to our proof of concept workflow. So what we do is we construct a proof of concept workflow where you use the common collective representation to compare different algorithms' performances using the AstraSim simulator. Traditionally, AstraSim would take input the chakra representation of the workflow and use its internal algorithm implementation, such as a ring algorithm or the halving doubling algorithm, to issue, send, and receive communications to the underlying network simulator. However, we extend the simulator to also take as input the common chakra representation of the custom collective algorithm and follow the algorithms as outlined in this representation. On the other side of this collective representation, we use the MCLang domain-specific language, which enables users to easily write their own custom collective algorithms. So to say it once more, this proof of concept workflow allows users to use the MCLang domain-specific language to write custom collective algorithms, lower it into a chakra execution trace representation, feed it into the AstraSim simulator, so that the simulator would use this collective algorithm representation to issue and simulate the send and receive operators. So here's a bit more detail as to how that works. The left image is a snippet of how you would implement a ring algorithm as part of the AstraSim simulator codebase. Whenever a user would want to test a new collective algorithm, they would have to create these implementations every time. This is not only highly cumbersome because users would have to know the simulator's internal implementation, but they cannot reuse this implementation across different tools or even the runtime library. The right part is a snippet of the input configurations provided when running the simulator. With our new extension and our new proof of concept workflow, users can simply point to the chakra graph for the ring for any algorithm, in this case, the specific ring algorithm. Users can easily swap between different execution trace graphs and also reuse them across not only AstraSim, but also across different tools. Once again, I would like to highlight that the chakra trace representation of the collective algorithms are not necessarily limited to the ring or halving doubling or the double binary implementation that the simulator natively has. Using the MCLang domain-specific language, users are able to generate their own custom collective algorithms and feed it into the AstraSim simulator. And also, users can also use other collective synthesizers, such as tacos, to generate their own custom collective algorithms, lower it into a chakra representation, and feed it into the AstraSim simulator. So this slide is a graph which shows the result of comparing ring and halving doubling on an all-reduce on a wide variety of topology and collective sizes. But one thing that I do want to note here is that this work itself is not focused on co-optimization or collective synthesis, rather is focused on providing a view on proposing that we need a common representation for collective algorithms, and the chakra execution trace is a good way to do that. What this graph shows is that we're able to build a proof of concept workflow that works, that allows users to further use this chakra representation to conduct further studies. And again, as future work, actually searching for the co-optimization opportunities and promoting interoperability between different tools to promote easier collective synthesis. These are all future works that we intend to do based on the collective representation that we propose in this work. So to wrap up, our work proposes that we use chakra execution trace, which is already being used to represent workflows, to extend that execution trace schema to also represent collective algorithms as a common representation. Yes, so that would end my presentation, and I'd be happy to take any questions.
Thank you. That was great. If anyone has any questions, a reminder to please place them in the Slack channel, which I will post in chat once more in case anyone joined late. So the first question is, are there any plans to extend existing simulators such as SST with Chakra?
So I'm looking at the Slack channel for that. So for the first question, I wouldn't be specifically for SST, not for me, not that I am aware of. The Chakra working group or the maintainers of the SST simulators might have their own plans, but as far as I can say, not that I'm aware of. Yes. The next question, can we take the example of a graph search and accumulate to elaborate on the idea of collaboration? Could you specify the question a bit more, Pankaj? I think, are you talking about like existing graph search works on different fields, I guess? If that's the case, then yes. Since we have a large graph, then I guess there are some implications where we could use these techniques and studies to further elaborate. Oh, I see. Let's see. Like DFS search patterns on shared graphs accumulating. So a high-level answer to that would be yes, we'd be able. I'd have to get back to that question a bit more later while I think up, come up with an answer in my head right now. To answer the next question, which I have an immediate answer to that. So the next question is it possible to create topology-aware collectives in Chakra? So just to highlight, Chakra is simply a representation of what the collective algorithm would look like. Right? It's a representation. So if we have a collective synthesizer that generates collectives, then Chakra is simply used to represent, hey, how are we going to have these send and receive? Like who's going to send to whom, who's going to receive from whom, and what would the dependencies look like? And so for creating topology-aware collectives, I'd actually like to point to Tacos, which is also another work from our lab. Now, Tacos is specifically aiming, specifically there for generating topology-aware collectives. So to provide a bit more of an insight, what we could do is we could use Tacos to generate topology-aware collectives, and then take the output of Tacos and lower it into a Chakra execution trace representation and feed that into an asterisk, which is actually a pipeline, another pipeline that we're actively building right now. But yes, that is a possibility. Hope that answers your question. Yeah, so that's the key beauty of using a common representation is that not only can we use the MSIC length DSL to generate these collectives, we could use Tacos or any other future collective synthesizers that come along the road. We can build a pipeline that goes from these collective synthesizers and lower them into the Chakra representation and feed them into wide number of downstream tools, whether it be the algorithm simulator or whether it be other runtime libraries once you build the pipeline.